So I'm César Puerta, and I work at Twitter.
My name is Dockter. I'm from Gradle. I'm the founder of Gradle. So today we want to talk about optimizing build performance of Android with Android Studio 3.0 and the latest version of Gradle and the Gradle Android plugin. And what I really like with this talk is that it's not like no sample projects, no test projects. It's one of the very important Twitter apps of the world. What was your experience with that transition?
Well, builds waste time, and I think that we will agree that anytime that you use waiting for a build, that's waste time. So how bad is it? This is our build at Twitter 1 year ago. 54 modules, one huge module, and a bunch of smaller modules. These were the dark times of AGP 2.2 and Gradle 3.1, and our times were awful. Let's say that we have 55 developers and 30 builds per day. That's like way too long. Let's say it's one full day waiting for builds every single day. So we have a number of challenges that are unique to Android. Fast iteration. We are shipping a new release every week. We just can't wait. We just can't stop to rebuild our build. Large code base with few modules. Annotation processing is pervasive, meaning that code size blows up very quickly. Builds are really complex and hard to understand. Who knows what's going on with those hundreds of tasks that are running in parallel? Performance bottlenecks and regressions go unnoticed. Sometimes you upgrade to a new version of Gradle, a new version of AGP, and all of a sudden your times start creeping up, and you may only realize when it's too late. And we don't really have a huge build team. We actually have one person in a build team that's part-time working on Android, and the rest of it is in the Android team. So we really can't afford to build a lot on top of the existing tools. And I imagine that a lot of people out there are probably in a similar situation. So that's where we were. In this presentation, we're going to talk about just some tips for optimizing your builds, how to monitor and understand your builds, how to debug issues. And I think that this is most important. When you run into an issue, how can you use the tools that you have in order to debug those problems? And finally, a few tips for optimizing the code base for build performance. So with that, Hans is going to talk about Gradle.
So I want to talk a little bit about the general improvements that have been made, the mechanisms, the tools that have been added, before then César continues with applying that to the Twitter build and look at the results. So when you look at the Gradle build platform, right, independent of the Gradle Android plugin, we have improved performance in many areas. It was our main focus, right? Much faster up-to-date checking, faster configuration time, faster startup time. It's 300-400 milliseconds. You might have not noticed, but we looked at everything, right? And faster dependency resolution. So that is an interesting one. So build performance and what affects build performance is very sensitive to your build. So faster dependency resolution at Netflix, where they have thousands of different source code repositories and everything is doing binary integration, dependency resolution was a huge bottleneck. So we brought build times down from 13 minutes to 2 minutes with faster dependency resolution. For your Android build, right, might be 3 seconds, right? So certain performance capabilities very much depend on the environment, how effective they are, how relevant they are for you. So let's focus on what was really important for Android. So if we look back, it's a little bit more than a year, right? So in 3.0, the daemon was enabled by default. And then 3.4, we've introduced compile avoidance, incremental compilation, and 4.0, the build cache, and 4.1, the worker API. So let's look at more detail about the effects of those features. So daemon by default, so I don't have to ask anymore who's using a daemon. It's now enabled by default. But I think it's still important to understand, right, what is happening here. Because I think, as you said, you don't have many people to kind of build upon a toolchain, but you should understand their behavior. So when you start Gradle the first time, right, Gradle is called and it fires up a server process, a daemon. And that daemon is not just a warmed up JVM, it stores a lot of state in memory, which will accelerate the execution of subsequent builds. So this is actually the build from Twitter. So whenever you see the bird, that means those are numbers from Twitter. And yeah, a clean build, 3 minutes. Now, this is today. This is with 3.0, right? Without the daemon, and this is with the daemon. So it's still significant. Of course, here execution time is dominating. When you have an incremental build, it's twice as long without the daemon and with the daemon. So one thing when someone is complaining to you, or the build is slow, have an eye on, is the daemon used, right? So, okay. Next very important feature is, it's actually a set of features. Compile avoidance, incremental compilation, Java library plugin. Compile avoidance, what does it do? With compile avoidance, when you have a module 2, that depends on the module 1. And you change the implementation of a method. So ABI means application binary interface. So a change that doesn't change the interface of a module, right? With compile avoidance, we still do a recompile of module 1, but we detect, hey, this is not relevant for the change for recompiling module 2, so we don't recompile module 2. And you can imagine in a larger dependency graph, that is a very effective feature. And it improves compiler performance, and it also improves the cache hit rate. We will talk about that later when we talk about the build cache. So, oops, that's a funny build-up. So the other thing we added as part of compile avoidance is the Java library plugin. You might have seen already in Android Cradle plugin 3.0, you can now assign dependencies either to an API configuration or an implementation configuration. Right? So what is this about? Right? So before, when you're not using the Java library plugin and your module 3 has dependencies on module 1 and module 2, when you compile module 4, is module 1 and module 2, will it be in your compile class path or not? It will be. The whole transitive path is in your compile class path, right? So, which is not very effective, because when you now change module 2, let's say the public signature, it will trigger a recompile of module 4. Compile avoidance says, well, this is a change of the interface, right? So, but when you now tell Gradle, hey, module 2 is an implementation dependency of module 3, it will no longer show up in the compile class path of module 4. And in reality, you don't have many API dependencies, you mostly have implementation dependencies. So that reduces class path sizes easily by order of magnitude, right? Yeah, everything, compile performance is much better avoidance, less to check for compile avoidance, and again, smaller class path means higher cache hit rate. Okay, so yeah, for Java projects, use the Java library plugin, and then use the API and implementation configurations and declare annotation processors properly in a processor class path. I will refer to some documentation to show you how to do it. And this is a very powerful feature. The other feature that is complementary to compile avoidance. So once Gradle figured out, okay, this was a change of the interface, right? Now we have to recompile. So what incremental compilation does, whatever you change, it analyzes the whole class dependency graph and decides which classes needs to be recompiled. So even module 1 is now not fully recompiled, and module 2 is only in as much recompiled as it is affected by the change in module 1. It's a more expensive analysis, right? So that's why compile avoidance comes first, and then comes incremental compile. So compile avoidance and also the cache hit rate, right? Because well, no, this is wrong. It does not affect the cache hit rate. So that was a copy and paste error. It improves compile performance, doesn't improve the cache hit rate. But there is a gotcha at this point. So in Java projects, for compatibility reasons, we will enable it by default in Gradle 5.0. In Gradle 4.x, you still need to explicitly enable it, right? And then in Android projects, it's enabled by default. In the presence of annotation processors, it's disabled per module. So when you have 45 developers, 54 modules, all the modules that use annotation processors will not benefit from these features at this point. Because we don't know enough about the annotation processors to understand how a change is incrementally affecting the output of an annotation processor, right? So this is work in progress, right? We are working right now on a solution to that together with the Google Android team, and this will be very, very beneficial once we have released that. It will be a solution that will be it will not be generic. There will be every annotation processor basically has to describe how its incremental behavior is, right? We will work for the most popular ones, right? But there will be an interface so that your custom annotation processors, you have some, right, can also make use of that. But you have to do some implementation work. If you want to understand this topic in detail, compile avoidance, incremental compilation, and the Java library plugin, there's a really, really, really good article about that in depth, right? One of the very exciting features that came with Gradle 4.0 is the build cache. And so to understand the build cache, let's start first in understanding the up-to-date checking in Gradle. You all know the up-to-date checking, right? When Gradle says the task is up to date. So how this works is, whenever you execute a Gradle task, it stores the hashes for the input and outputs of that task on this. So the next time you run the Gradle build, we calculate the current inputs and output hashes, right? And for the compiler, it means your class path, your sources, your compiler version. And when this is the same, the task is considered up to date and not executed, right? So, one thing we also do with that feature, if a task is incremental, we tell the task, hey, those are the input files that have been removed to avoid stale output. Those are the input files that have changed, so that you can easily now write an incremental task. In any case, what the up-to-date checking is offering you is it reuses build output from the last time you run this build on your machine. And we have now added another layer on the cache, on the reusability of output, which is called the build cache, where first of all, it's not just from last time, from any time you have built, right? You can use the output, and not just on this machine, but from anywhere. You can now share build output. And that is a very important performance accelerator. So how does it work? When Gradle considers a task out of date, it uses the same input and output information to calculate a key out of the input. And then it asks the build cache, do you have output for that input, right? And if not, it will execute the task and stores the output in the cache. And otherwise, it will retrieve the output from the cache. So a typical setup is that Gradle comes out of the box with a local cache. And usually the local cache, the local cache is very helpful when you switch between branches, right? For your dirty working copies, right? The remote cache, usually developers don't write to it, they only read from it, and CI, where you have a more controlled environment, writes to the remote cache. And that is a very effective feature to accelerate CI builds as well as developer builds. You need to enable it, right? At a future version in Gradle, it will be enabled by default, but at the moment you need to enable it, right? And it's very configurable. So a couple of more things about the build cache. So any of your custom tasks, you can use the cache API, they are cacheable. Java, Groovy, Scala, 2 channels are cacheable. Android is in 3.0 cacheable, but there are some issues, so you need to apply some workarounds. You will talk about that. We expect those workarounds to go away with the 3.1 release. Who was at KotlinConf? Great show, huh? So you might have heard already about that. We expect cacheability for Kotlin very soon, right? The Kotlin team is maintaining the Gradle Kotlin plugin, and we're working together on that. So stay tuned. If you want to understand more about the input-output model in Gradle, up-to-date checking, and the build cache, this is an excellent guide to read. So, and here are some numbers, right, for Twitter by using the build cache. So this is a clean build with no cache and with the cache. We can make, this is an amazing improvement, but this will get better even over time, right? And of course, for the incremental scenario, right, when you change one line of code, the build cache is not helping you. Okay, so last thing of the new features is coarse-grained parallel execution. Who of you is using -- parallel when building Gradle? So check this out, right? It's project level parallelism. It's usable with Kotlin. It has a strong effect on your build time, especially with Android Gradle plugin 3.0. The parallelization efficiency has been much improved, right? So one problem with that is, and that is why it's not enabled by default, you can do some stuff, right? That if you don't configure your Gradle build correctly, the way parallelism works with -- parallel, it's hard for us to detect. So you have to pay attention to that. What we have introduced in Gradle 4.1 is the new worker API, right? And that enables immutable, very guaranteed, a safe, guaranteed, reliable parallelism, and a much more fine-grained parallelism, right? So you can use that for subtask parallelism or for intra-task parallelism. It's enabled by default, so you can use it for all your custom tasks. It's used partially at this point in Android Gradle plugin 3.0. The Gradle core plugins starting to use it, and the Kotlin Gradle plugin is also starting to use it. So out of the box, you're not getting many benefits from that, but there's now much better infrastructure there, and over time, this will be used much more by all the standard plugins that you are using. Okay. The Android Gradle plugin 3.0, there are excellent presentations, right, about all the work that went into that. It's an amazing job the Google Android team did, right? Much faster configuration time on the Android-specific configuration aspects, many memory and speed improvements, better incrementalism, better parallelism. You want to learn more about that? This is from Xavier, the presentation, this one, the Gradle Summit, and this is from James at Google I/O. Okay.
So until now we've been looking at the builds as the build tools that you're getting out of the box. Now, for the next section, we are going to look at how to understand your builds and what tools do you have for understanding your builds. And there's going to be a quick overview of the tools that you have for monitoring your builds before moving on to talking about how you apply them in practice to figure out your own build issues.
Cool. So one thing you can do, you can run Gradle with -- profile. Who knows about that? -- profile. Right, so it's pretty, generate a report and build reports profile, list timing for configuration task execution, right? So it looks like this. Get a summary, right, where the time was spent. You see which tasks were up to date, how long they took.
You didn't have a designer at this time, right?
That's right. But there's now a much better way to see what's going on with your build, and that feature is called build scans. So you can run, starting with Gradle 4.3, you don't need to configure anything. Before that, you need to apply the build scan plugin with 4.3 that is built in. You can run any Gradle build with --scan. And then, depending on your setup, it will either send a build scan to the Gradle Cloud Services. It's a free service, right? You need to agree, right, that we upload that, or like Twitter, you have an on-premises version of Gradle Enterprise where you publish it to a Gradle Enterprise server. And let's talk about a build scan that you can upload to the Gradle Cloud Services. So this is when you run a Gradle build, you get a URL at the end of the build. You can click this URL and you get to this view, right? And yeah, design has improved. And
yes.
And you get tons of valuable information that helps you to optimize the build, but also to detect problems why your test might have been failing, right? So from a developer perspective. So you have a timeline view, right? You can understand the parallelism, right? And obviously we see some potential for improvement here, right? And you have a lot of querying opportunities, right? You can filter all the tasks by certain criteria. Of course, performance is a very important aspect of build scans, right? How effective are tasks avoided, and which tasks are spending most of the build, using most of the build time. And it's by design a deep collaboration tool. So for example, if you're wondering what is your dependency situation, might a dependency be responsible for a failure that you're having, right? You can dive deep into the dependency graph, and for all the views you have here, there are deep links, right, that you can send to someone, and the person will get exactly the same view. So it's a very helpful collaboration tool. And you can extend it, right? So you can add your own tags, you can add your own custom links, for example, a link to a div that captures what has changed in your dirty working copy compared to the last commit. So you can provide a lot of context for someone to analyze what is going on. When task has failed, right, you get the whole context of the task failure. And let's talk quickly about Gradle Enterprise. That is a version you can install on premises. Soon there will be also hosted instances of Gradle Enterprise. And here you have access to all the data, right? So you have a search view. You can say, hey, show me all the CI builds that have failed, and much more. You can do build comparison. Why did it, and you will show that later, why did it succeeded locally and failed on CI? And you can use the export API. So this is an example. Tableau is using Gradle Enterprise, and it did some amazing analytics, right? With the export API, pumping the data into Tableau. The big rectangles are compile tasks and test tasks, for example, right? And the bigger they are, the more failures they have. And then the inner rectangles is a specific compile task of a specific project. So you get a really good idea where are the bottlenecks. And Gradle Enterprise also ships with a remote cache backend, right? Multi-node replication will be available soon. So yeah, and one thing you would do with Gradle Enterprise, you would enable publish always, that you really collect all the data, every execution, every Android Studio, Gradle execution, command line execution, CI execution, you will collect all the data, so you have a really good idea about the build experience all your developers have, wherever they are. Okay, so now we're getting into even deeper territory.
Yep.
Oh.
Yeah, I'm going to be talking about a couple of lower level tools, like the Gradle Profiler. So the Gradle Profiler is this open source command line tool that you can use for running your builds. And what the profiler will do is it will run your build. This is a command line. It will run your build, and it will give you a Chrome trace, for example, of your builds, which you can just configure like this. You would say, this is my project, and this is the scenario that I want to run. I want to profile a non-ABI change to see how fast it is. So this is what a scenario looks like. So you would say, this is a task. This is the file that I want to change in order to emulate a change in that particular file. These are just a couple of configuration arguments, and these are a number of warm-ups. As we mentioned earlier, the daemon makes a huge difference. So the profiler will warm up the build before it starts taking measurements. And this is what you get. So if you're familiar with systrace, you will find this very familiar. You're getting here the CPU occupation, and this is the heap. And these are all of the threads and all of the tasks that we're running on each one of them. And you can see for each one of those what sub-operations that we're running. So this is giving you a lot of detail. In some cases, it will not be enough. So what's happening, that long task down there, what's taking most of the time there? And in that case, you will want to use just a regular profiler like YourKit, for example. So YourKit, you see, it gives you a lot of detail. Here, for example, it's showing you that Dockter is running, so you can see how long of your compilation time is taken by annotation processors. You can see some more detail here, like the distribution of operations to different threads. And setting it up is relatively straightforward. So you can just go to your Gradle properties and add to the JVM properties of your daemon this line is saying, I want you to load YourKit as soon as the build starts. And you would say, I want to do a sampling profile, and I want to save a snapshot of memory at the end of it. And that's it. That will give you the snapshot. An option is to use the profiler instead. So this is a super convenient way to get a profile of your build. It will run your full build using that scenario, and it will produce a snapshot at the end. One last tool that you have is to use the logs. Now, ideally, you don't want to do that, right? Since logs are incredibly verbose, and I've seen that there are a number of other things. But if you wanted to know, for example, what parameters are you passing into the compiler, right? Well, the logs would give you just that. You can look at the info logs, and you would see that the boot class path, the processor class path, there's a ton of other information. But this is in particular one very useful piece of information that you will not find anywhere else. And these are the tools that we have. Now, in practice, you may find your own issues, and you need to figure out how to use these tools in order to address them. So this is what this next section is about. I'm going to look at a number of issues that we've been running into at Twitter as part of our work in optimizing the build, and walk through how we have used these tools to solve them in the hopes that it could be useful to you. So a very typical issue is up-to-date check issues, or these days, I guess that we would say caching issues. Since the problem here is that you run a build, you run the very same build a second time, and you get a rebuild. Why is that happening? Or you run a build in one machine, and then you run a build in another machine, and you get a number of tasks that are rerunning, even though they were cacheable. Well, if they're cacheable, you would expect that every single one of those tasks would be reused, right? So how would you figure out why is this task running if nothing changed? Well, there's logs, and you can look at the output of this task, and that would tell you what properties changed. I mean, no one does that. The most convenient tool that you have is build scans. It doesn't have to be great at enterprise, but you can use build scans if you want to find, for example, in this case, tasks that were successful in spite of being cacheable, meaning these are tasks that run even if they should be in cache. You can go into any one of those tasks, and you can look at the properties that changed. Like this is telling you that the compiler args changed. So now you can go to the logs, as I mentioned earlier, and you can see what's changing between the compiler args. Or you may get this other option. Well, this is not really saying anything. This is saying a bunch of directories were deleted. Yeah, the build, this was actually in build, so of course I know that. That if you wanted to know in every single case the reason why a task was rebuilt, what you would want to do is do in Gradle Enterprise, you would do a build comparison. And that will, you can pick two builds. You can pick the original build and the build that should be getting everything from the cache. And you can compare those builds. And that will tell you that the source changed, the source of the compiler arguments. So this is the fastest way to figure out those issues. In the past, it was almost impossible. I mean, it was not worth the effort trying to figure out these issues. But now it's very easy, and it really pays off to spend some time trying to understand if you have any one of these issues. Now, I'm going to show you a bunch of issues, typical issues that you may run into, so that you see that this is actually something that happens every day, and this is not something that the tools will necessarily solve for you. Indeterministic code generation. This is a very typical one. So you may have something like this. This is the build config, and the release time in it. That's changing every single time. That's making your application potentially non-cacheable, which is a huge waste of time. Another typical issue is you may be writing your own annotation processors, and you may not realize that some of your code is non-deterministic. You have a list of things that depends on the order in which you're loading them from disk. And now it turns out that these files are different every time that you build that you do a new build. Another potential issue that's similar is non-relocatable artifacts. This is you build something in this computer, then you would expect it to be available in this other computer that has different absolute path for files, and it doesn't work. That may be because you have absolute paths as part of your build, which happens also more frequently than you would think. Here's in this example, you would see the comparison says the compiler args are different. Now, if you look at the args, well, yeah, it turns out that we are passing an absolute path to an output file into our annotation processor. That's breaking incremental. It's breaking the caching for that artifact as well. So, sure enough, that's the code. You can replaced with something like this. That's a utility function that we wrote. But you get the idea. And that would fix it. Similar problem, AIDL generation. It's embedding the absolute path of the original files in the generated files, which is, well, I guess that made sense, but not anymore. You're using caches. So that's another bug that I'm hoping that Google will fix soon. Other issue that may go unnoticed is empty directories. An empty directory is actually a file in your input. So if you have an empty directory that may have been left behind by Git as you delete files, you may find, well, the exact same problem, that your source is different. Now, if you were to compare the two trees, you may find that that's the only thing. Grader will take care of this at some point, but for now, you should know that empty directories will cause this problem. And finally, you may have corrupt or invalid artifacts in your cache, meaning that your build is failing when you're building it from the cache. Otherwise, it's working well. So, in order to figure out what's going on, you may use this nice feature in Grader Enterprise that will allow you to go from any cached task to whichever other task that produced that file. So that will help you figure out what was the build that produced this artifact. That's not what I was expecting. And then I guess that you could do this, right? Just get rid of the cache and be done with it. But that's not a great idea because, if this artifact is in the remote cache, the problem is certainly not going away. But there are a number of other things that you can do. You can certainly run without the build cache, or you can fix the issue in the task that's producing the artifact, which will invalidate the existing artifact since the cache key will change when you make these changes, and that with that the problem will be gone. And in the case that the task is not something that you own, that you cannot change it, then what you can do is just disable the caching for the task, which you can do just with this simple snippet. And just for every task of that type within your project, you would disable the cache. And that's it. Finally, Hans just mentioned that there are a number of bugs in 3.0, that are sort of breaking remote cache in a number of ways. It's actually significant. If you were to fix all of those bugs, you get a significant improvement. Grader collected fixes for all of them, while 3.1 ships. And well, you can enable like this. There is this plugin that you can apply to your Android projects. Will fix all those bugs. In our particular case, just applying that increased our hit rate in the remote cache from 70% to 80%, which is pretty good. So, other type of issue, memory issues. And this happens all the time. Your build is super slow, and it may just be that you're spending a large part of your time in garbage collection, right? So, you would see it in the profiler like this. It would tell you that's garbage collection, and it would say, hey, you're spending most of your time in garbage collection. Or you can go, you can look at the scan and the performance output. You can see that's 35 seconds in garbage collection, which is quite a lot. So there are a number of things that you can do for this problem. You could potentially increase the heap size. But this is not going to solve every problem. If there is a lot of garbage collection, increasing the heap size may potentially just increase the duration of the process, but overall the time that you spend in garbage collection may end up being exactly the same. So an alternative is to fork compilation, since that's one of the greediest tasks that you have. So this may be another option. The compilation process will be turned down altogether, and Gradle is using a separate process that stays alive for the duration of the build. So it will start all of the builds in the separate process, but at the end of the build it will tear it down. And finally, if you have a leak, you can use YourGit, for example, to find it. So like I mentioned earlier, you would set up the daemon to run YourGit and to collect a memory snapshot at the end of the build. And this is And this is what you get. You can look at the snapshots, and you can go to object dominators. An object dominator in your kit is an object that's solely responsible for retention of a large amount of memory, of objects in memory. So in this particular build, you can see that the merge resources task, and this is taken from an early alpha of 3.0. This is fixed now. But the merge resources task would be holding 1.5 gigabytes at the end of the build. And drilling into those tasks, you can see that the inputs, the resources were loaded into memory and kept in memory until the end of the build. So this can happen. Typically, you don't have to fix Google's bugs; they will figure them out. But I mean, it's good to have the tools, and you may run into similar bugs. And also, well, if you do find bugs in the Gradle tools, you may as well report them. And they do a pretty good job at responding, so you should really do that. Slow execution times. That's a similar problem in the sense that your build is doing something. It's taking too long to run your tasks. It may be memory, like I mentioned earlier, or maybe something else. We are using, for identifying regression, which is the first step. We are using the export API in Gradle Enterprise, which allows us to dump all of the data for each particular task into a MySQL database that we can then look up using Zeppelin. So we are using software that's available freely. Here you can see, I mean, these are a lot of lines, right? But in that particular point, that's the average duration of the lint task that at the time when we deployed beta 5 shot up by around 2 minutes. And this is because there is a bug in that particular beta that will generate an APK at the time of running lint. That will get fixed soon. But I guess that what's meaningful here is that we could pinpoint where this happened very quickly by looking at this. So you can now, in other cases, you can use the profiler again. Here is a good example of a huge duration for the configuration that we can't explain. You can go into your kit, similarly as we did earlier, and you may see in our case here that this particular checkstyle task was taking forever. Anyway, moving on. Moving to the thing that we are running short of time, so I'm going to race through the last couple of sections. Debugging Gradle, this is the last resort. You may want to attach to Gradle, to attach to the AGP, and actually figure out what's going on. Now, that's actually quite straightforward. In the case of Gradle, you can just clone Gradle, start IntelliJ, just like this, then run Gradle in debug mode, and attach to it. And that's as easy as it gets. Using a remote configuration, as you typically do with a unit test, for example. Debugging the daemon, you may want to do if you wanted to debug a behavior that's only happening during, let's say, the sync time in Android Studio. So you can do that as well. You can just update your global configuration for the daemon and say, I want the daemon to listen for debugging request, and then you can just run your build and attach to it from Android Studio. If what you want to do is debug AGP, and when I say AGP, you may want to debug any tasks in the Android plugin, or you may want to debug your lint rules or your checkstyle rules or anything that's running inside of your build. You would do the exact same thing. You would start Gradle in debug mode, and you would attach to it in Android Studio in this case. And this is as easy as it gets. As it turns out, Android Studio knows the version of AGP that you're using. It can fetch the code. It will automatically allow you to attach. So it's extremely easy. In the past, when I run into issues with lint, and sometimes those can be infuriating to debug, I would just do this. I would figure out the exact issue, and I would report it along with a screenshot of the debugger at the point of the problem, and that gives you a fix much quicker than anything. Finally, you may want to patch AGP if you want to try something, and this can get tricky. You wouldn't want to build all of AGP. So there are alternatives, and as it turns out, Gradle has this thing, has the build source directory, which will compile anything that you put in there and will put it ahead of anything else in the class path when running Gradle. So if you were to copy any classes from AGP into build source, into your local build source directory, and put them in there, you can make any changes that you want, and you will see them in the output. So this is it's as simple as it gets to patch bugs or to patch issues in AGP and try out those fixes. Finally, please do report the bug. Finally, the one last thing that we all run into is low parallelism, and it looks like this. You have 4 workers, and you're using 2, or in a build scan you would see a similar thing. This is depressing, but it's a typical build. Like, you have a lot of small modules, and then you have these large modules sitting at the top that's taking a majority of the time. In order to fix that, well, there's not much that the tools can do, so you have to modularize. And it so happens that there is a talk right after in this room on this same topic. So it will improve compiler performance, compiler avoidance. It will optimize caching of build artifacts. It will optimize parallelization, better code architecture, lots of reasons. For some advice, I could say, so you would want to use API dependencies sparingly, of course. Isolate annotation processing. Hans mentioned earlier that annotation processing disables incremental compilation. That has a huge cost. So if you can move annotation processing outside of your main modules into smaller modules, you can save a lot of time. Remove bottlenecks in your graph. You don't want to have one single task on which one single module on which every single other module depends, right? Use Java modules when possible, since they are simpler. And finally, make use of refactors and underdistributable resources. There are a ton of other things that you can do. You can do dependency injection, you can do dependency inversion, and there are many, many other things. Like I said, someone else will talk about it later today. Wrapping up. This is where we are now. We went from 54 modules to 115 modules. Still one large module, and we are now on the latest versions of both AGP and Gradle. And this is what our build looked like in June. This is June versus last year. So clean builds, they went from 5 minutes to 2 minutes and a half. Incremental builds went down to 13 seconds, and this is for building the APK with a fully warmed daemon, but still, it's quite impressive. The latest version, we regressed, and this is because we enabled Java 8, and the Sugar task is not incremental. So that's throwing a wrench in the whole thing. It's still pretty fast, but that's a work in progress. Still, if we add the build cache to it, our build times, they're quite impressive. They're much faster than they used to be. So yeah, there's still work to do, right?
Still work to do, absolutely. So on your side, on our side. So as I mentioned, one thing we're working on intensely is incremental compilation with annotation processors. So that will be a very impactful feature, and stay tuned, right? So faster incremental builds, well, in this case, it's mostly that regression, right? But in general, there is more incrementalism. For example, check style is not incremental yet. So there are quite a few tasks, where you can step by step improve the incrementalness. And that will particularly help organizations with larger modules. Higher parallelism, as you said, modularization is key, but at the same time, even though for the example you showed, we will not get to 100% utilization, we might, with more fine-grained parallelism, we might get it up 10-20% to what it's now, which is nice, right? So memory usage has much improved, but 34 seconds garbage collection time is not where we want to let it end, right? So we constantly improve build scans in Gradle Enterprise. So we will also add more and more strict nodes to the Gradle input and output model that we will try to avoid as many pitfalls as possible, right? That you have described. Higher build cache, hit rates. How would we get there? In terms of on the Gradle Android tooling side? Well, yeah, of course. Some tasks are not cacheable yet. That will be cacheable in the future. Right? For example, the DEX transform task is not cacheable yet for various reasons. Right? Reliability comes first. We need to invest a little bit more work, and then the cache effectiveness will probably significantly increase just by that one task. And then who suffers from, who is really kind of suffering from Android Studio sync times? That's only 10%. So the rest is happy with Android Studio sync time. Oh, no, I mean, seriously. Yeah. No, the thing is, right, we're talking here about the 115 submodule builds, but there are many Android projects that have...
It is painful.
You know,
painful.
No, but it depends on the size. So anyhow, it's a big focus, right? So that is another area where you can expect progress soon, right? Some stuff is already in master, but it needs to be merged. So that's it.
We're much better than we were, but we will get better. So if you have any questions, that's all for us.
Yeah. So the question is, are there guidelines how large a module should be? Because we've seen build where there's one source class in one module, right? And that's, I think, not the way to go, I suppose. Not for Twitter, at least.
Yeah, no. I think that we're looking into different criteria for how we break down our modules. I would say that you would want to break them down functionally, typically, or by layer. I think that what we typically do is grow our modules as we add more functionality to them, and then as we find that they become a bit too large, beyond, let's say, 200 classes or something like that, we look for opportunities to break them down any further. You probably don't want to go from the very beginning into writing lots of many very small modules, since that's going to be very hard to manage, right? You just need to do that incrementally. This is not something that you can do in a big bang. You will break things off incrementally. It will naturally grow as you go.
Thank you very much.
Scratch your chin.